So, I'm Levent Alexeyenko from the Budapest University of Technology and Economics, and I will give a short talk about how can we validate a parking lot assignment method with the help of Eclipse SUMO. At first, let us see mm, what is the benefits of autonomous vehicle parking. At first, it does not require any human supervision, so it can save some time for us. It can provide denser parking, so fewer parking spaces are required, or the parking capacity can be increased in this way. We can also optimize the parking costs, but it can also add to the traffic demand. Therefore, cities may limit the distance of this empty cruising for parking lots. Uh, to achieve these goals, we have to make a parking lot assignment method that is able to provide us efficient matching of parking lots and autonomous vehicles, and it can also help to lower the traffic demand. To define such an algorithm, a parking lot assignment algorithm, we have to assume something about the future. For example, we can assume a 100% traffic penetration level for convenience. We can also assume that every autonomous vehicle is now privately owned or long-term rented. And we can be sure that parking and distance-related costs will also endure in the future. And we can think about that everyone has a free parking option somewhere in the city. For example, everyone can have a home garage, even it can be very distant from our actual destinations. To solve the parking lot assignment problem, we can apply a single unit demand simultaneous auction method, where parking lots are trying to sell their free parking places, and autonomous vehicles try to book an auspicious parking place somewhere in the city. The benefits of this method is that the protocol, I mean the auctions, converges to optimal solution. Uh, it makes possible the distributed computation as well, and it can be efficient in terms of computational time and memory complexity, because both of them can be done in linear time and with linear amounts of memory. So the major advantage here may not be this, but that individual valuation of parking lots is also possible. For example, we can define parking lot utility functions. For example, we define here a formula which consists of two parts. Basically, first term expresses that we count the parking prices and the distance to get these parking prices, and we introduce a free cruising parameter, a weighing factor between parking prices and moving distances to a given parking lot. So it is trivial that an autonomous vehicle has to compute this parking lot utility function to decide which parking lot shall be bid for. And for example, here we can minimize this utility, or let's say this utility function. In this algorithm, we can define three parameters. As we can see, there's a free cruising parameter, the weighing factor of this auction mechanism function, and there can be a municipal regulation limiting this empty cruising to parking. Of course, we are having some measures to evaluate, for example, the total parking cost, which is trivial, and somehow it also reflects the usage of parking lots. And of course, from a traffic point of view, the empty cruising distance is a very important measure. That is the aggregated distance traveled by empty autonomous vehicles in one day. The question is how to validate this method. It's a hard question, a little bit provocative one, because we need multiple complex traffic scenarios, road network of 4 cities, thousands of vehicles in it, which results in high computational time. But the main problem is that we know very little about future urban or traffic infrastructure. Therefore, specific data of today and available simulation tools may obscure the results. Therefore, we can assume that cities can hold their basic shape. Therefore, we can formulate it somehow mathematically and evaluate this mathematical model to overcome these obstacles. Our concept of validation is therefore that we have an abstract city model given with probability distributions, and we are trying to solve the mathematical problems as a simulation here, which is controlled by the auction-based parking lot assignment mechanism, and we will receive some validation data. To evaluate this, we also have to define comparable SUMO scenarios and make simulations with it. And at the end, we can make consistency testing. About consistency testing, I think that the abstract model shall result in an optimal range for some parameters, but when we are simulating a concrete model in Eclipse SUMO, this parameter range has to be at least as strict as the results we are obtained from the abstract model. From a technical point of view, Eclipse SUMO is controlled by Tracy, where the auction-based parking lot mechanism is simulated in Python module, and we are requesting movements of vehicles in SUMO between two parking lots. To have a comparable scenario, we have a very basic human activity model. This model is so simple that it can make so it makes comparable the mathematical problem formulation with the Eclipse SUMO. So we have two basic activity types, working and shopping, and the most common activity chains are simulated. For example, working and shopping activities or something like this. Our abstract city model is pretty much like a pizza. It's two-dimensional. It's a circle statistical city model described by probability distributions, and it can contain curbside parking lots and park and ride facilities around the perimeter of the city at different locations and with different prices. This model is free from detailed road network because we know very little about it. And to have a realistic distance between 2 points, we make a DD measure, which is a random factor of an Euclidean distance between 2 points of the city, and some random variable, which is something like the detail ratio. We have to also define a SUMO scenario comparable to it to obtain validation results. So we extracted OpenStreetMap data of 11th district of Budapest, Hungary, with NetConvert tool, which was also able to recognize P+R facilities in the city. After that, we used Zaga to generate trip chains, but we only kept the origins and destinations because we didn't want to cross-validate Zaga with our basic abstract activity module, activity generator module. We have to make a comparison in the auction mechanism. So the covered area is almost the same as the SUMO network is rectangular, but we have some parts that are not simulated colored in as white here. So the network sizes are about the same, and we have curbside parking lots in the abstract model in the city center, and here we have a downtown area depicted as brick red with dense curbside parking lot distributions, and P+R facilities around this downtown area in the 11th district of Budapest. And in the abstract model, these parking houses are located on the perimeter of the city. In the abstract model, we focus activities to the city center. Here we have the downtown with numerous points of interest, and we hope that Zaga is able to generate many activities concentrated into this area. The parking capacity is also an important factor here, and we made sure that the two scenarios are operating with approximately similar parking capacities. So let's see the results we obtained from the simulations. At first, let's see the abstract model-based results of empty cruising. We can see that when we set the distance regulation low, high empty cruising was observed because our default movement was to return the AVs to their home garage when they cannot win a parking lot, for example, because it is out of range with a low distance regulation. We also we can find an optima between 2 and 4 kilometers, and we can also see that if we value the parking prices more than the distance to these parking prices, we also get higher empty cruising distance. We also measure this metrics in SUMO results, and interestingly, we found that when the free cruising parameter is low, therefore cars are trying to park near their destinations, it also results in a high cumulated distance, which is interesting, and we will see the causes of it. But we can also see that a low distance regulation in a real-world scenario not necessarily increase the empty cruising distances because parkings are focused near the activity locations in a real-world city. Okay, the total parking prices can be questioned when we use an auction mechanism, but I'm happy to announce that with this mechanism, the average daily parking charges remain in the acceptable range. It is pretty much the same amount that we have to pay nowadays for a 8-hour parking in Budapest. So what we also can see that free cruising parameter shows negative correlation with the parking prices. It's not surprising, we expected this result. SUMO results are pretty much the same, higher CFP results in lower parking costs, and we can see that when the distance regulation is below a certain level, numerous alternatives may be out of range, and this can be seen in the decreased total parking prices. But these trends are stabilizing between 2 and 4 kilometers, which was the optimum settings of this parameter in abstract model-based results. As I mentioned earlier, the lower CFP values resulted in higher empty cruising distances, and we think that it is mainly caused by many cars that are trying to find parking lot in a relatively small area in the SUMO scenario, and we can see it as a lower average speed when this parameter is low. We can also observe that the curves are pretty close to each other when the distance regulation here is in the optimal range, and we can also expect that or we want to have a predictable algorithm. Therefore, we have to constrain the free cruising parameter into this interval. Therefore, we are basically consistent with the abstract based model optimum. All in all, we can see that a certain level of empty cruising distance regulation is required to reach free and closed parking lots and to avoid this congestion forming in a concentrated area around the downtown. And of course, if we are applying an auction-based parking lot assignment, which has a weighing factor in it, it also has naturally has a positive correlation with the average speed, because when we are allowing cars to explore the whole city for parking lots, it can be done with higher average speed, but also it can cause a negative correlation with the parking prices. So empty cruising distance shall be governed by municipalities in the future, and to evaluate autonomous vehicle mechanism, we can use abstract models, Besides, more detailed simulations with Eclipse SUMO shall be also applied during the validation phase as it can enrich our previous results. Uh, that's what I wanted to show you today. So thank you for your attention, and please free to ask me questions.